Okay. Okay, so good afternoon, ladies and gentlemen. Let me introduce our guest, Matteo Caggio from Institute of Mathematics from Czech Academy of Science. We should say something a little bit about you. So he did his PhD with me in Institute of Mathematics. Then he moved as a postdoc to University of Latvia under supervision of Donatella Donatelli. Then he moved to University of Zagreb under supervision of Boris Moha, and finally he came back. And now he's in our institute as a researcher, and today he will speak about a very interesting subject, between low and strong stratification regime for rotating heat conductive fluid. So, please.
Thank you, Chef, for the introduction. Good afternoon. So today's talk will be about stratified fluid. I will be, during the talk, I will specify to you what I mean about low and strong condition about the stratification. So we are in the heat conductive setting, and for fluid, they are under rotational frame. So So this is a work, joint work with Gabriele Zweig, our colleague in Trieste, and it's basically, in some sense, an extension of a previous theory that Gabriele developed during his PhD, during also some postdoc positions. So we worked together in the last couple of years about this potential extension. So I will tell you more in detail what I mean about it. But let's start with okay, let's start with the model. So this is an Stokes Fourier system, and it's under what is usually called rescaling. So the blue parameter are respectively the Rossby number that is taking care about rotation. So it's a balance between how much inertia and rotation they play in the fluid. The Mach number limit related to the presence and potential of acoustic perturbation, and the Froude number, that is the ratio between inertia usually and buoyancy forces in the fluid. So is related to the fact that we have a gravity, at least in this kind of setting, a vertical gradient, a vertical force gravity. So we are in a strip R2 times 0, 1 with the full slip boundary condition. So this is our model, and we wanted to study some particular regime when this number they are pretty small. So I ask you why gravity x cubed? No, it's not. Sorry, it's x3, the third component. Okay, it's an insect. No, you are right, Miller. I put it there because yes. Okay. No, but of course it's a good question. So I never noticed that is the third component. Sorry, you are completely right. I will, because I put E3 but not X3 down. Sorry. You are no, but you didn't ask me this last time anyway, so maybe it was okay. So it's just, I mean, you have a strip, okay, slip of the complete slip condition, gravity in this way, okay. So we rescale the system with respect to this number. The viscosity of the fluid is fixed, so we don't have any vanishing case, and this is important because I will tell you that there are differences respect to the technique that you use to treat this kind of limit. So the setting where we are is the following. So we fix the Rossby number. For example, you take a parameter epsilon that will go to 0, and you assume, for question of speed of going to 0, different kind of rate for the Mach number and the Froude number. So, and the point is how we can play or interplay between these three parameters in order to have a proper limit in the sense of between state of the strong stratification and the low stratification. So it's not written above, but the state of art concerning the result. So let me write here just to be precise. So that the Mach number is scale like epsilon to the power m, and the fruit of number, the scale of sign to the power n, just to don't come back in the slide. So about the state of art. So there are several results in respect to the type of scaling that you are using between the Mach number and the full number. So one of the first result in this, the first result probably in this direction concerning the scaling is when in fact you have the Mach number or the effect of the Mach number that is dominating over the Froude number, and typically you end up in the two-dimensional setting because you have also the rotation that is creating a two-dimensional flow in the limit. You end up typically, at least in this context, with a 2D Euler-Boostner system, means Euler equation plus a transport equation for the perturbation of the density. In a moment that this number, let me say, dominates on this number respect to the speed. If you have the same scaling, if you have a similar scaling, but you don't scale the stratification, you end up in what is usually called quasi-geostrophic system. And the reason is that the Mach number in this case and the Rossby number, they have the same scaling. And typically in fluid mechanics, when the Coriolis force given by the rotation equilibrates the pressure force or vice versa, you are in what is called usually quasi-geostrophic or geostrophic equilibrium. So when you have m equal 1, independently of the relation that you have here, you have the same scaling, in fact, of the Coriolis force. I will show you more in detail what I mean about this later. And when you have the same equilibrium, you end up in a quasi-geostrophic system. Both of these results, in particular, the second one is without the scaling of the stratification, so without this guy scaled, so this is fixed, it's not going to zero. They are developed for a vanishing viscosity fluid, vanishing viscosity in the fluid through the usual co-relative energy method. But it is not, they didn't touch by this method the endpoint case n equal m over 2. This was done indeed by Gabriele, Francesco Fanelli, Daniele Del Santo, Anita Wróblewska-Kamińska, quite recently. So changing basically the technique, but treating viscous fluid. So they were able to study the endpoint case n equal m over 2, where m is or equal 1. And if it's equal 1, with the same philosophy like before, you have the quasi-geostrophic system. When m is bigger than 1, you end up in this case in what is called 2D Overbeck-Boostner system that is not the Euler system, because in this system you keep the viscosity and the heat diffusivity of the fluid. So you don't have a transport equation for the temperature in the strict sense, but you have also the Laplacian of the temperature. The same for the Navier-Stokes part. This was, the technique, typically usually called compensate compact argument, give them the possibility to treat the endpoint case in what is called usually low stratification regime, namely that the Mach number over the Froude number is going to 0 as epsilon is going to 0. So basically the Mach number still dominates on the Froude number. They don't scale with the same speed. So this is what was basically the summary of what was done up to now in that direction. One point was, okay, I have m over 2, and potentially m is equal than 1 for the quasi-geostrophic limit. So if I fix m equal 1, can I go over this limit? This is the point of our analysis and the result that I will show you today. So this work was indeed done already in case of constant temperature, and we were wondering to extend it for heat conductive fluid. And this was we done in this analysis. And somehow the challenge that we found was that in the process of the analysis, you have some singular terms. So some terms that they scale like epsilon to a power less than 0, and that they were not present before. And these terms indeed are a consequence of this choice. So we wanted to go over 1 over 2, but still below 1. That means that still you are in what is called strong low stratification regime. So m will be 1,
n will be less than 1, so you still are in the low stratification, but not for fixed n equal 1/2, but for a range of low stratification that stay between what is usually called strong and low. Strong when you have this number strictly equal to 1, because when you rescale with the same number here, usually you call in the literature strong stratification. When this number is below this 1, it's low stratification in the sense that Mach over fruit is going to 0 and epsilon is 1. So somehow we are still in the context of low stratification, but the critical, going behind the critical scaling gave us some terms somehow to treat that they are singular in the first input. So this is our result. Sorry if I bring you immediately to basically to the theorem. So what we are able to prove indeed that in the low Mach number limit, in the low fruit number limit, so the presence of the stratification, and in the low Rossby number limit, you have in fact a two-dimensional dynamics, and your system satisfied a quasi-geostrophic equation written both for the momentum in terms of the stream function, is typically way to write the quasi-geostrophic system in 2 dimensions, plus the analogous for the temperature. So in fact, you are dealing with a stream function Q that will be solution indeed of your quasi-geostrophic system written in that sense, where this Q is indeed the perturbation of the density and of the temperature that you have in the limit. So which are the difference with somehow the previous work? Somehow there is a slightly difference with the previous analysis developed by Gabriele and his co-authors, in the sense that when we fix really the case n equal 1/2, you characterize the limit dynamics respect to, let's say, density variation with respect to the constant target profile. In the case of behind critical regime, is respected to the static density profile. I mean, maybe it doesn't look a bit different, but somehow when you are fixing here n equal over 1/2, somehow you are able to show that your dynamics is really a constant target profile of the density. In this case, still you could have dependence of the X3 variable. Moreover, there is somehow, let me say, a technical difference between our analysis and previous analysis. So the stream function that they have here has also a dependence on the gravity that is in the third component. So in order to have a stream function respect to the perturbation of density and the temperature, you should have another age respect to the vertical variable that usually we are is denoted by the brackets. So this I will show you later what I mean exactly by this. So believe me up to now that this is an average respect to the vertical variable. And also you end up with a sort of non-homogeneous boundary condition for the part that belongs to the temperature variation. So in other words, respect to our results, where we have a different kind, let's say, of more natural boundary condition for the temperature variation, and a stream function that doesn't include the gravity. So it seems to us somehow more natural to end up with this kind of system respect to the other one that still concern the presence of the gravity that typically we use in a two-dimensional setting. So this is somehow a remark about the difference of the work developed before, still for the fixed n, respect to the work developed for heat conductive fluid when you are behind this critical scaling. So, so now I wanted to start somehow to tell you more in detail how it works, this kind of analysis. So I'm supposed to remove maybe this
Yeah. I think okay, it's okay.
So I just wanted to have the title of the slide. So there are some, up to here, I'm not discussing really how to pass to the limit. It's just a constraint of the dynamic. So I told you that in fact the dynamic is two-dimensional. Indeed, this could be shown. So then if you have a family of weak solution related to some initial data with some property, in fact, having a limit point of your sequence, then you can prove indeed that this limit point is a two-dimensional dynamics. So and this is the reason why, I mean, this is coming from the fact that when you have the Rossby number that is going to 0, so you have a sort of fast rotation, and all your dynamic became a two-dimensional, you lose the velocity in the vertical plateau. So you can prove, in fact, this. And in fact, you can also pass to the limit. I mean, you can show as a first step that you can pass to the limit in the continuity equation, giving to you, in fact, the divergence recondition for your velocity field, for your target velocity profile. Up to this point, and this is the limit that we do it week in our continuity equation in order to get indeed one part of our limit system that is divergence free. But concerning the fact that we have a constraint on the limit passage and giving the balance between indeed the Coriolis force and pressure perturbation, you can show in fact that your dynamics is in fact bidimensional by this condition. So in other words, you pass, for example, if you take a continuity equation, then you have to pass to the limit, of course, also in the momentum equation, in the entropy equation. But by formal limit constraint, you are able to say that your dynamics will be two-dimensional, given in particular by this balance. The same balance that I discussed with you before when I mentioned the fact that when these two numbers are in balance, you have the quasi-geostropic limit. So equivalently, I mean, you can write the second equation there that is telling to you indeed by your boundary condition that in fact you end up with the third component of the velocity equal to 0, and everything is a two-dimensional dynamic. So now the point is the two slides before was the limit passage in the continuity equation, so you have enough good a priori bound that they give you the possibility, and also compactness argument that they give you the possibility to pass in the limit in the continuity equation. The question is how to do it for the momentum. So I will not go in detail about all the tools that we have and also all the potential limit passes that we have concerning all the terms that they are linear in the momentum equation, but I just wanted to discuss about the term that indeed is the most interesting one that usually is difficult to pass to the limit in the nonlinear one. So basically you have to pass through the formulation of the wave or the acoustic system related to your Navier-Stokes system. So this is an analogy of this system. I didn't write all the definition of the terms that they are here. And by this analogy, using this analogy, you can handle indeed the convergence of the convective term, because inside this term, like inside the other one, however the other one are easier to treat, you have the presence of potential oscillation respected to the vertical variable, and you have to kill them, basically, to remove them in your limit, because you want to arrive in a two-dimensional set. So you write this kind of system that will, let's say, help you as a tool in your analogy in order to pass to the limit, in particular with the convective term. This system is written for a suitable modifier SM that is smoothing your solution. So somehow we are using this because for technical reasons we need some smooth control of this quantity. And this is exactly what we want to do. So we wanted to study the limit in the convective term written in the weak formulation for epsilon that is going to 0, and then for the parameter of the modifier that is going to infinity to remove the effect of the modifier. So in other words, we needed to pass this just integration by part that you lose the part on basically on the far field condition. So we want to pass the limit in this term, and to do this we need our acoustic analogy. So you can write this term, and here is coming the other edge. So here is more subtle. You can write this term in the sum of two terms where there is the horizontal divergence of the product of the average plus the divergence of the average of the product. What I mean by this, so if you take, let me say, so U, E, Uj, and you want to average this quantity, but every UE is, or Uj, is exactly the sum of the average plus a potential fluctuation. Respect to this kind of definition, so an average in the vertical sense. So when you applied all the average to the nonlinearity, the cross term, you remove the cross term, they disappear because the average of the fluctuation is zero. So you end up just with these two terms in the end. It's something that you can also find in the Reynolds, typical Reynolds decomposition for averaging. I mean, it's the same philosophy, but done in the vertical sense. So you have to treat these two terms. In particular, the most interesting one is the first one. The second one I will skip. And so you can prove that the second one is going to zero, indeed, for epsilon that is going to zero. The question is, how do we treat the first one? That in our point of view is indeed the one that contains the singular term that we have to treat it in the limit. So you use the acoustic system that I mentioned you before, so you can rewrite the first term by a combination of some quantity called gamma in this level. I am speaking now smooth quantity up to now, so in order to handle these steps, plus a sort of reminder that you can prove that in a weak sense is going to zero. For example, could be some gradient, perfect gradient quantity, and for divergence precondition test function, this is going to zero. So you can treat the first term in this way, you can rewrite it in this way, and then the question is, in which way I can handle gamma? So I have gamma multiplied by the quantity V there, that is smooth, is my limit function, okay? So I can write gamma in that way. And again, from the acoustic system, I'm able to write the terms that belongs to gamma, or I do a step back about V and Z in that way. So this is through the acoustic system, okay? And exactly there, we have to handle the two singular terms that they appear in our analysis. The reason is that I wanted to end up with a quantity that is written with respect to the time derivative of gamma. So I have some bounds for gamma. I need some bounds for the time derivative in order to apply, for example, Aubin-Lyon's lemma. But I needed to get rid about the color term, that they are the singular term that they came out from our analysis. So basically 1 minus 2 times n is less than 0. So for epsilon going to 0, indeed they explode. So the second one is pretty somehow clear because inside G, however, I didn't read anything before because it was a long list of formulation, there is the gravity. So if you arrange respect to the vertical component, you lose immediately this term. It's basically straightforward. The other one is more complicated. So somehow we're lucky on the fact that you can relate the other one again through some basic quantity connected to the gravity field. So you are able to get rid of both of them for the property of the average. So I mean, it was not obvious from the beginning. You should somehow compute and to see if indeed you end up with a reasonable quantity that you can treat algebraically with this average in order to get rid of it, independent of the fact that they are singular. So if you sum up, you see that you sum up and you have this relation. And you can use the property that you have on gamma by a priori estimate and so on in order to have, in fact, a convergence in the sense of distribution of this quantity. So you have L2 weak convergence of your velocity coming from the a priori bounds, and you can prove indeed that gamma, you can prove it that gamma converges strongly in the space. So you have, in fact, the convergence in the sense of distribution. And by definition of gamma, indeed, you are able, in fact, to, maybe it's a bit misleading, but to show that indeed your velocity v is in fact the smoothing of your indeed velocity in the limit by definition. And this z belongs indeed to the smoothing of the perturbation of the density, perturbation of the temperature that they are connected to the string function in the limit. So all the philosophy was, I need a convergence of some suitable quantity in a suitable way, sorry for the repetition. In the first step, I have everything smoothed by nullification. I have enough control on this quantity in order to pass to the limit and to identify this quantity with the proper one. In this case, V indeed is the smooth U is the limit of my system. And in fact, I can pass to the limit with epsilon to 0 in these two terms. And one term will go to 0 directly, because this is a scalar, this quantity is a constant. If you apply the definition respected to the string function and you integrate by part on a suitable test function that is divergence-free condition, so you lose this term. And the other one, if you come back with the algebra by the definition used, you can prove indeed that is going to 0. Sorry, not going to 0, that is going to the proper limit. So in fact, however it's not written in the same way, you can identify with the second term the limit of your nonlinear term in the Navier-Stokes equation, in the Navier-Stokes system. This is a backward step from the algebraic point of view. I can show you the detail of the paper. So you lose this is 0, and this indeed is your proper limit of your nonlinear part. So you end up with this also with m that is going to infinity because it's smooth enough, and you can backward go with the computation. So, and in fact, considering your two-dimensional dynamic, indeed you really can, for a proper choice of your test function, you really can identify the limit in the nonlinear term, and with a similar argument, but easier because they are not the same nonlinear contribution, also in the other part of the equation. So you can pass to the limit in the weak formulation, and this is exactly the weak formulation of the quasi-Jastrowi system in your limit. The same, you can do it with the entropy equation. Sorry if I didn't put many details, but it's strongly technical, all the steps. So I just wanted to give you somehow the idea that is behind this procedure. So you basically construct a constraint on the limit dynamics. You realize that your limit dynamics is two-dimensional for the reason that I told you before. Then you implement an analogy of your Navier-Stokes system with the acoustic system that is helping to you in particular to treat the nonlinear term. And because your dynamics from the constraint a priori is two-dimensional, you introduce a proper test function that you can do it in this way in order to give you the suitable structure to pass to the limit. In fact, it's not the case that your test function indeed is given by the same string function that I discussed you before concerning Q. So this was basically the point. So the novelty of the work is I have singular terms respect to the barotropic case when the temperature was fixed and was constant. I'm able to do it, to treat it. Yes, I'm able to treat it in the limit. I'm able to pass to the limit and to end up with a quasi-geostrophic system of equation. So which are the open problem and potential of the future research direction? So one problem that is still open also for fixed n equal 1, basically, is what is called strong stratification regime. So when Matt and Freud, they scale with the same epsilon, so you have an order of 1. And in fact, it seems, at least for our knowledge, that this vertical oscillation that you are able to kill through the procedure that I described you before, they persist. They seem to persist. So you are not able to put them to 0, in other words, roughly speaking. If you add the centrifugal force, so the modulus square in the horizontal component, so you have a rotation of your fluid and you have a centrifugal force in this direction, you can treat the case, they treated the same paper, the case with m greater than 2, because it was the proper scaling to treat the centrifugal force by some technical stuff. But there are 2 open problems. First, if you are going between 1 and 2, it seems that f is too singular, so it will blow up in the limit of epsilon that is going to 0. And also the limit point, the profile density is not constant anymore. And this seems that is giving to you still problem with the vertical oscillation. I don't know too much detail about m equal 1, but anyway, it seems that you are not able to close the machinery. The future direction that we are working now with Daniele and Gabriele is to implement the centrifugal force to end up with a different kind of system with respect to the quasi-geostrophic one we are studying in this direction, but still we are behind the critical scaling in a proper scaling that will respect anyway our low stratification regime. So independently of this part, this is what is really, it really counts for us. So the fact that we are still for this range, you can still be behind the critical scaling. This is basically one more step, maybe humble step, to introduce the centrifugal force in our system. So one next step that we are working now is I wanted to stay in this behind critical scaling. I want to introduce the centrifugal force, but the machinery that I have to use here is for sure m greater than 2 in order to treat it with the same technicality that they use in the previous paper, and also to have a proper behind critical scaling here. So this is what we understood up to now. So it could work in this direction. It will be potentially one small step with respect to the analysis done up to now, but we wanted to try to see if with the centrifugal force and with the same system, anyway, we could have a potential reasonable result and interesting result. So, and that's all from my side, and I thank you for attention.
Thank you very much for the lesson. So let's shoot some remarks addition. The last.
Just to the centrifugal force, so usually if you have a constant axis of rotation prescribed, so then it is it can be involved into the gravitational potential. Consider.
Yes, but anyway, you have the scaling from the Froude number also there. So it's rescaled also the gravitational potential is, if I go really from the beginning,
Yes.
you have anyway the scaling there. So potentially you can improve it. But anyway, there is scaling also there, so that you have to handle it. And I don't know which kind of rate to give it to him, honestly.
Okay, decide.
No, you just.
Standard data are potential. So
Yes, standard details, but in the moment that you rescale it, the question is which proper scaling you could have in order to close. Because as far as I understood from Gabriele Daniele, the problem is that there is a moment in which something explodes because you don't have the proper scaling in your machinery. This is roughly speaking. I mean, of course, you have to go into the detail of the proof. But was similar problem like the singular term that we had. As I said, we were in some sense lucky because we had the proper algebra to treat all the singular term in terms of the gravitation. And because you average in the vertical component, the gravitation disappeared. This was the point in math. But it was not about scaling in that case. It was about the algebra behind the structure of the system.
This is.
No, okay,
So,
just to
No, it's
try to
fine.
reply to you.
More questions? So can you show me once more the limits of n? Okay, so you have some quasi-geographical system.
Yes, yes.
Just put it.
I was not precise here. Here it is an average of some quantity that they remain on the right hand side. Something that usually you don't have in other kind of analysis. But the remainder of the terms are the typical quasi-geostrophic equilibrium, where of course here, differently from Rotary and Maltese and Kvon, we don't have the vanishing viscosity. They have it because they have a relative energy inequality approach. They should send the viscosity to zero. In our case, it's a weak convergence. And we keep the viscosity in the limit, of course, we can't really push it.
Another question, but I don't remember. There is some paper about this. There is thousand. This is Gerard Barret and this lady.
Gallagher.
Yes, Gallagher. And they also treated some relation between Mach number, Brock number.
Yes, they have the barotropic case, as far as I remember. They have some rate here of the Mach number respect to the Rossby number. Some rate to have more incompressibility in the limit or less incompressibility in the limit, but it's barotropic. And I don't remember, I think that there is a presence of the Freud number, but I think it's still low stratification. If I'm not wrong.
Yeah.
I don't remember all the combination of scaling, but yes, they have something in this direction that is barotropic.
Yeah, because I was thinking that maybe to generalize it.
Yeah, okay, but I don't remember. I think it's they still have.
They have something between n and n.
Yeah, they have it, but I don't remember exactly the point. But it's not beyond the critical scaling.
Oh, it's not.
This
Yeah.
no.
But they have some too.
Yeah, this paper of Edward Isabel and Gerard Barret was indeed mentioned in the paper of Gabriele, Francesco, Aneta, and Daniele when they did the first analysis.
Yeah, maybe you should also say why you are using this oscillation and all these things, because you have this initial data, all this not well prepared.
Not well prepared, yes.
You feel prepared, and then this is the difference between well prepared and well prepared. So if you have error, then it means that you need this acoustics, right? To kill this oscillation. So this is why for those basically.
Anyway, Sharp, in this kind of context, we prescribe initial data such that they can develop a wave, of course, but then this splitting is what is giving us the possibility to remove the vertical oscillation in the end.
Okay.
But of course, the initial data are prescribed in ill sense, as you said, in order to have the presence of the acoustics wave or the wave in general.
Yeah, okay. Yes.
Thank you for the talk. Can I ask a stupid question? So with centrifugal forces, what would you have as partial conditions? Because I imagine why does everything just fly off to the cylinder?
This is a very good question. I don't know if I have the answer. I mean, in fact, you have in the unbounded domain, you have it up to. The question is that we are studying how to treat exactly this point. I mean, because you have, of course, something that is going outside. If I remember properly, you compensate with something else. But of course, if you write a modulo square of fixation, you have it in all the three.
What I remember also in systems that like have itself gravity, then you even form, or then density even tends to accumulate in a layer.
Like in stars, right?
This.
Yeah, and this. Yes, if you treat the cell gravitation, you should change
Because anyway you are going to cross G.
You should change something in gradient of G to include a potential self-gravitation. Yeah, it could be an option. Yeah.
But even when I was out that, what would, even without self-gravity, but just having gravity in this, but then this destabilizing centrifugal force, what could prevent something like this from happening?
So you mean
If
this?
you have self-gravity, so then if the mass is put into the infinity, you will slow down the rotation, so the angular velocity is going to zero.
Potentially, yes, but I don't know. So I'm not able to reply. But thank you for the remark. It could make sense to introduce potentially the self-gravitation. Yes.
So the angular momentum should be present.
Exactly. Yeah. Exactly. Yes.
Because this self-collapse is potentially possible, but strongly one should prevent it by making P dependent on rho in a way that it will be sufficiently big blow up if rho goes to infinity. So I think Shaka has it in some of their articles.
Anyway, I want to reply to you also somehow in another way around. The point here is that your two dimensionality you reach because the Rossby number is going to fail.
Yeah.
So if you fix the fruit, so you don't do anything with fruit, you keep sort of, so you say, okay, I have the gradient of some force, or some potential, sorry, it's a force, it's fixed. Maybe you can also say, okay, it has all the regularities that you want, I don't care about it, okay, it's just an external component. If you fix a fruit, you can go with the Rossby to 0 and somehow you have the two-dimensional flow. Anyway, okay, you have in a way the quasi-geostrophic equilibrium. When you put the fruit, you have to see the balance, because in a moment the fruit equilibrate Mach means you have a strong stratification. Seems that in your acoustic system or wave system in general, okay, you are not able to kill the vertical oscillation because the fruit indeed is not small enough respect to Mach. It's a technical issue, you know. And this problem is still open as far as I know, also in the barotropic case when the temperature is fixed. So you don't have necessarily entropy equation like I have it here, the last one. So it's a technical problem respect to the killing, sorry for the word, of the oscillation. And this is independent of the fact that you have indeed a two-dimensionality. You can also remove Rossby completely. You can have the strong stratification, and anyway you could have some problem about it. This is the reason why we introduce this and we play with this, because in the end, our system is two-dimensional, and you don't see anymore the average because you are already in this dimensional setting.
Yeah, but the one point is that it's like a bounded domain,
Yeah.
which means that you need some partial position.
This is stuff that I didn't mention. We have, in fact, a bounded domain that I didn't mention this, I'm sorry for this, that is enlarging to infinity faster than the acoustics oscillation.
So you start with bounded.
I started a bounded domain. Sorry, I forgot to mention before I was distracted, but you have a bounded domain. This bounded domain is going to infinity faster than your oscillation.
Something like
A sort of, but is inside the definition of the domain.
okay, then this you don't need.
Yes, I don't need, no.
Then you don't need it, but you need some rate of expansion.
You have a rate of expansion that is faster than the rate of the oscillation that you are killing in the limit. So you don't really need a far field condition in this. It's a trick, it's just a trick that they used before, I mean, it's technical stuff.
No, it's technical stuff. Okay. You are, yes, since you are not going to order, you are not using this around dependent, okay.
No.
It's okay.
I want to finish to reply. In the previous work, they had to implement the average because your string function is still depending by a vertical variable. So it makes sense to them to say, okay, I have an average resulting in my stream function, something that here we don't have. We don't have because we have a different scaling. It's not n equal 1/2, it's above, it's beyond, sorry. And this is helping us somehow to don't have g in the stream function. I don't want to say that it's wrong to have g there. It's in a way a scalar function. You can, q is defined by scalar quantity, and q is a stream function by definition. It's a stream function in the usual Euler sense. So you can write two-dimensional Euler. This is not just okay, but when you write two-dimensional Euler in the sense of stream function, has the same meaning, q, of the stream function of Euler. Okay, just written in a different way because you have density and temperature. So we don't have it here. Is a slight difference, of course, but it counts for us because somehow we don't need to apply the average. We don't have a result in average for the stream function. And also there is a difference in the boundary condition that they are more natural in my point of view what we have. And if you want, there is a difference also in the limit that you have. Our density, in fact, is a static density profile, so could still depend on the vertical variable. In the other case, it's a completely constant profile. I mean, it's a difference, maybe tiny, but anyway, it's difference. More the fact that we have a singular term to treat that in the barotropic case, and it was not written, because this job was not done for the Leo in critical scaling. It was done before for n equal over 2. We wanted to go over it and to see that we can do it indeed and to compare the result.
Some more questions about seems to be not the case of I think next week we will start on holidays. But something close to holiday and Christmas, so I wish you Merry Christmas, Happy New Year, everything the best for next year, and not only next week, but after next week and forward. So see you in January. Or February. I don't know if we do something for January, I'm not sure. We will see. Anyway, enjoy for you.
But you are this for.
Thank you so much.
No, sorry.